this talk is about a muon collider, so let me start introducing you the muon. So the muon is a lepton, is what we call a second generation lepton, is somehow the heavier cousin of the electron, is electrically charged, and has a mass which is about 200 times the mass of the electron. But other than that, it's very similar to an electron. There is another very important difference, which is actually a key point that you will see throughout all this colloquium, that the muon, in contrary with the electron, with respect to the electron, is actually not stable. Muon is an unstable particle. It decays to an electron and neutrinos, and it has a proper lifetime of about 2.2 microseconds, so not very long. And this has profound implication when you want to build a collider out of a particle that actually decays pretty quickly. And we'll see that basically a lot of the challenges are connected really with this lifetime. But without running too much, let me just go back a little bit about these constituents. And as I was telling you, colliders have been pretty instrumental in this center in understanding this building block. And in fact, here, essentially, I wanted to highlight that out of these building blocks, the majority of them were actually discovered through colliders. And so this basically highlights really how this fundamental understanding of nature has been paved by collider experiments. And at the core of how we use collider is essentially the scattering of particles. So we want to essentially make particles interact or scatter to each other, and based on the information about the initial and final state, understand the dynamic, the forces that govern those interactions. And essentially, those particles that I showed were discovered at Collider. There were sort of two types of experiments that were going, either what we call fixed target, when a beam of particle hit something at rest and then produces some outgoing particles, or what we call collider beam, where you have two beams of particles that essentially hit each other. There is profound differences in the available center of mass energy of this type of collision, and this is pretty important because essentially we can use this type of scattering in two different ways, I would say, broadly speaking. One is to produce new particles. So out of this reaction, we might produce new particles. And the mass of the particle we can produce is directly related to the center of mass energy of this collision. So the maximum mass we can produce is essentially related to the center of mass energy available in this collision. In our idealistic case, in the most ideal case where all the energy can be converted into a new particle of some mass. But then the other thing is that this type of reaction, being purely a quantum mechanical effect, they are probabilistic. So what will happen through this scattering, not something that you know for sure. What you know is the probability of some reaction to happen, okay? And there are many, many different types of reactions that might happen. So to study and produce new particles, you also need to have enough rate of reactions such that the probability of producing the particle you're looking for is large enough to be observed. Okay, so this is another key point of collider physics. It's not enough to have something that is high energy. You need to actually to repeat the type of scattering experiment many, many, many times. And it turns out that, of course, the most interesting processes turn out to be also pretty rare. And so this is what is basically shown at the bottom, the number of events being proportional to the probability of that process happening, or what we call cross-section, and how many collisions you manage to get together, which we call usually luminosity. The second way that we can do that is actually though to study indirect effects of new particles. And this is an interesting way because it gives us some sort of leverage. So it turns out that in looking at rate and kinematic of some of these scattering processes, this rate and kinematic can actually be influenced by particles that you don't have enough energy to produce, but they can still influence the rate of processes. So this is sort of what is schematically shown below, in which the scattering to particle might change the rate or the probability of determining a final state, even if the particle in question has a mass which is higher than the center of mass energy of your collisions. And so this dichotomy of sort of this double way of producing a particle or looking for indirect effects essentially is the main ways we look for fundamental laws at colliders. So talking about colliders, what are the highest energy colliders we have at the moment? And this is the Large Hadron Collider that is located at CERN in Geneva, near Switzerland. This is a picture. The collider is actually underground, about 100 meters underground. Has a circumference of 27 kilometers, so from one end to the other is about 5.3 miles. And this is a collider where collides protons that are accelerated essentially to a speed very close to the speed of light, and they collide with a center of mass energy, which is 13.6 tera an electron volt, which is essentially an energy that corresponds to about 14,500 times the mass of the proton. So if in the most idealistic case, although the reality is a bit different, we could, in principle, create a particle that is as massive as 14,500 times the proton. Now, we don't collide one proton at a time, just because what I told you before, we need a high rate of interaction. We need to look for rare processes as well, so that would be pretty inefficient. In fact, we inject about 2,000 bunches, each of them having about 100 billion of protons in the machine at the same time. And then those get to collide about 10,000 times per second, each of these bunches. And so these basically produce on average about 100 million proto-proton interactions per second. And this has been going on since 2010. So to make that happen, it's something that requires a huge effort and huge international collaboration effort. And in fact, we have essentially more than 10,000 scientists around the world and about 2,000 from the US that are working on this project. So this is a pretty big endeavor, but it's worth the effort. And while there is so much of the physics that I'd love to tell you about, I'm just gonna show you a couple of things. One is simply in the upper left is essentially how many papers the ATLAS collaboration, which is one of the major experiments that I see, has produced through the years. And you see that essentially we have produced more than 1,400 papers that have been published in peer-reviewed journal, which means around 100 papers per year. So these are large collaborations, but the physics that we are after is also really broad. And that allows essentially a large number of publications. And this is back to the same thing as was said before. Each proton-proton collision is a sort of story by itself. You only know probabilistically what will happen, but each type of reaction that happens gives you access to a different type of physics. So studying different type of reactions, we can actually study different type of fundamental physics. And so one famous example is the discovery of the Higgs boson, which is essentially related. It confirms sort of the mechanism explaining why the weak force has such a short range. And as a bonus, also actually explains why the fermions matters have an inertial mass. And this is the type of plot that we show where we essentially illustrates the probabilistic nature of these reactions, where the points are essentially the rate of a specific type of reaction that has been isolated. So how often has been seen in our detectors as a function of some kinematic quantity of your final state. In this case, it's the invariant mass of the final state particle. And that blue is essentially the events that we attributed to a Higgs production, to a reaction where a Higgs was produced. And this basically confirmed a theory that was firstly developed back in the 60s, experimentally confirmed at least in 2012, and there was a Nobel Prize given for these theoretical ideas in 2013. So this is an example of the finding new particles where you can actually produce a new particle and see evidence of that. But in addition to that, we really have hundreds of precision measurements of different types of reactions, many of which, dozens of which, have never been seen before. And this really forms the richness of collider physics. And in addition to finding new particle, we also can exclude theoretical prediction when a particle might be expected from some theory, but is not found. So this is all beautiful, but in the field, we know that we are far from done. There are really big questions that the current theoretical and experimental understanding of nature is just currently not being able to answer. Here are just some of them. Things like why we have more matter than antimatter, why the antimatter has gone away, or what is in general the origin of electroweak scale, or the weak scale, or the scale of the weak interaction, and so on. And so I just wanted to give you a few examples of why we are thinking of a Muon collider in this specific case, or in general, future collider beyond the LHC to explore these type of questions. And so I will start with one, which is a sort of one that you might have heard of, which is the nature of dark matter. Dark matter is something that we have observed cosmologically from measurement from, for instance, rotational curve of galaxy. We know it's something that exists, but we actually have no idea exactly what it is. Not only that, even more puzzling, we have excluded any known particle we have produced and found in this collider. Any of these particles, we know it cannot be responsible of dark matter. So finding the nature of dark matter is what we think a high priority question for the field. And in particular, it's not only finding evidence of dark matter, but it's essentially being able to produce it in a laboratory setting to be able to study its property and property of other particles that often we expect to appear in a similar mass scale. So this plot is a bit complicated, but essentially it shows as a function of the possible dark matter mass on the x-axis, and then on the y-axis, essentially for a relatively common assumption that a dark matter particle might actually interact weakly as well. And depending on the properties of this particle, it shows what is the reach of a Muon collider in terms of being able to find such a particle. And then the black lines show essentially a prediction for the mass of this particle that is compatible with what we observe from cosmology. And so essentially a Muon collider of about 10 TeV scale is able to probe for essentially all the reasonable assumption if a dark matter particle is indeed a particle that is weakly interacting, which is one of the leading hypotheses. Another example that I wanted to show you is the origin of what we call the electroweak scale. So it's the scale at which electromagnetism and the weak force is sort of bind a bit together. This is really related about the Higgs mechanism. So this is sort of, I mentioned the Higgs as about this mechanism that explains why the weak force has a short range, and it gives also inertial mass to particles. But the reality is our theoretical understanding of it and our theory is essentially the simplest possible form of that theory that can be made. We don't know if it is the correct one, we just know it's the simplest possible form that is compatible with data. And a key part of it is essentially, as in any theory, the potential that governs the dynamic of that field. And so this potential is a quadratic form, and if you want to make this theory work, this potential, let me see if I have a pointer, maybe? No, fine, that's okay. That works, thanks. So to be able to work, this potential has to have a very specific shape, which is this white line. And in particular, critically, it has to have a minimum which is away from zero. The bands show you actually how well we constrain this measurement right now at LHC. So you see we actually, many different potential forms can be possible and may be very different from what is the simplest possible form. It turns out that actually measuring this is extremely difficult because it involves very rare processes that only happen at very highest energies. And in fact, even by the end of the LHC program, this is the best sort of, again, the bands will be our uncertainty that we can measure this so far. Crucially, we don't even know where it will cross zero, and we have no idea if some other minima can be developed. And so this is where sort of higher energy collider like a Muon collider can excel in essentially measuring this potential. And if that wasn't enough, this actually is connected to very profound questions about how the electromagnetic and weak force came together and actually split apart to manifest differently. And in fact, if you go back in the evolution of the universe, at some point, the temperature of the universe and the energy scale was high enough that weak and electromagnetic force were the same thing. Everything was essentially massless. And then this split happened at some critical temperature. But the way it happened is a sort of phase transition, like in matter when we pass from a gaseous to a solid or so on. So if that phase transition was a smooth transition or was a very bursty transition with bubbles forming around the universe, we have no idea. And this is something that only this type of higher energy collider can really shed a bit of light of what arguably is the most fundamental phase transition we know of has happened. And even more, we actually don't even know if we have other minima of the potential that that this field could jump into through tunnel effect, which could change the nature of essentially our universe in a heartbeat. This is actually something that might be happening, but we have no measurements of why that would be possible, or if so, why it hasn't happened yet. So in addition to that, the last example I wanted to give you is a little bit special in the sense that in addition to trying to look for sort of theoretically motivated scenarios that try to explain existing phenomena, we always need to be prepared for something that is unexpected and just keep a broad experimental program. And so the most obvious thing is looking for new forces. So new forces we have seen, like we can look for like strong like forces, so we can have composite objects, things that we think are elementary that in reality are composite and are bounded by a new force. One of the most interesting examples is the Higgs boson itself, being the only fundamental particle we know so far that has no intrinsic angular momentum, no spin. It brings up the question if that is really an elementary particle. We had cases before in particle physics where we had particles that had no spin, and they always turn out to be actually composite particles. So is the Higgs different, or is that a composite object? And this shows you that essentially, as a function of the mass of the scale of this composite particle, you can explore essentially what the LHC can explore is a sort of up to a few TeV in compositeness scale, and then anything that goes beyond a new collider like of a Muon collider 10 TeV and so on can explore up to a much larger scale. And other proposals of new collider were summarized in this dashed line. So actually a Muon collider really excels in this type of measurement. Or we can have a new weak-like force. We in a very lazy way, we call it Z prime, just to repeat the same letter we know about. And this again, the gray band is essentially how much we can probe the scale of such a new force with the current colliders, and you can expand through a Muon collider to much, much larger scales. So this gives you sort of just a little bit of an overview of the type of program we are after. And in fact, there are really plenty of extension of the current theories that try to address some of all or part of these questions. And they do it usually predicting new particles, often at high energy scales, but they may show up in very different way. So most point to a higher energy scale, but the specific prediction they do can be wildly different. And that's why to be able to prove as many of them, we need sort of a program, and we need an experimental program that has to be broad. That is sort of the breadth of the experimental program, I think, is the most important part looking at the future. So having something like collider, like higher energy colliders, offers really the opportunity to link different type of reaction to different possible prediction. And this is what gives us the best possibility to essentially explore in the broadest possible way. Okay, so I talked so far a little bit about why we essentially want to high energy, why we want to probe rare phenomena. Well, but I haven't really told you of why would you really want to do a Muon collider. In fact, so far, we've been colliding mostly electrons and protons, okay? So if you want, not very fancy, this is what our atoms are made of, and plus they are electrically charged. And this has been going pretty well so far. So here you can see essentially as a function of the year and the center of mass energy. In different colors, this has been electron-positron collider, and this has been hadron collider. And we've been able to scale them to higher and higher energy. So why do we need to change at all? Can we just keep going? And in fact, there are a couple of really good reasons for that, for which I wanted to sort of remind of a couple of basic concepts of how we accelerate particles. So this is one of the ways we accelerate particles. We call it what we call synchrotron, in which we have groups of particles, a bunch of particles that go around the ring. And then when they go through some specific elements, they get a small acceleration. They go around and then accelerate more and more and more. Okay? To go around, you need to curve them, so you need to bend the trajectory, and that is done through a magnetic field. So these are the sort of these red elements. So you accelerate, bend, and repeat many times until you reach the highest possible energy, which is driven by your magnetic field to contain, and then you bring them to a collision. And at that point, you detect what happened in that reaction. So there are a couple of effects to keep in mind here. One, that is, you need to bend these particles. So for bending, you need a magnetic field, and you need, and so to go to higher energies, meaning like to accelerate this particle to higher and higher momentum and velocity, you will need to be able to keep that in the ring. So you either need a bigger ring and you need stronger magnets. And so that will limit essentially how much energy you can accelerate to. The second thing is that we need to accelerate charged particles because we need to be able to bend them. But a charged particle that is accelerated emits radiation. And the power it loses by emitting radiation is proportional to the momentum over the mass at the fourth power. So for an electron, actually, this is essentially the limit of accelerating electrons in these rings. They lose more power than we actually can put in as we try to accelerate them. Lucky enough, both a muon and proton is significantly heavier than an electron, and so the fourth power means that this type of phenomenon is negligible in those cases. So back to this plot, essentially, the limit of this scaling for electron-positron collider has been in circular collider that we need just, it is a too much large power loss due to radiation. While in the case of hadronic, essentially the challenge to push this line further is that we need stronger magnets and larger rings. And in fact, to be fair, there is actually a plan that is being looked at to actually do exactly that, to build at CERN an even larger ring, which would be about 90 kilometers in circumference, which can use this even stronger magnetic field to collide proton instead of about 14 TeV to a range that goes to 50 to 100 TeV. And that's one way we can push that line a little bit further. But there is one other thing to keep in mind, which is what we are really colliding. So when we say that we are colliding protons, for instance, protons are not an elementary particle. They are made of a soup of quarks and the binding constituents of the strong force, so the binding carriers of the strong force, which are gluons. So when we collide protons, we are actually colliding part of their constituents. And this means that only a fraction of the center of mass energy of the proton-proton collision can actually be used to produce new particles and create reaction we can study. On the contrary, when we collide electron and muons, to a good approximation, all the energy of this elementary particle goes into the collision and allow us to essentially study what we need, the reaction we need. So this boils down to a very, very rough equivalence, I would say, that a 50 to 100 TeV center of mass collider with protons is roughly equivalent to a 3 to 10 TeV collider, for instance, as muons. There are a lot of caveats, but roughly speaking, to give you an idea, that is a rough equivalence. And that has a profound consequence into how big of a collider you need to achieve the same physics goal. So this is an example. This shows essentially how the size of the ring of LHC compared to the size of a muon collider of about 10 TeV, which is similar, and how it would compare to a size of a ring of about 100 TeV. And not only it has implication in sort of civil engineering construction, complexity, but there's also implication on power consumption, where a muon collider essentially, given the more compact size, will have a power consumption similar to the current LHC. A little bit higher, but in the same order. So the small footprint and intrinsic type of sort of acceleration technique make a muon collider actually a pretty attractive options for this reason. And in addition to that, it makes it, if you go back to that line, essentially is the difference between pushing a line a little bit further and if you want to start a new line in that plot with a different type of collider. So investing in understanding the technical feasibility of such collider essentially can give us a tool that would be flexible and will allow us to essentially think even beyond this current target of energy. Okay, So this brings me to essentially how do we realize that? So if that's so appealing, why we haven't done it yet? Why it's not has not been done yet? And in fact, the idea of a Muon collider is not new. It's something that was proposed. The first ideas are back even into the 70s. And then I'm more serious, let's say, thinking about an actual accelerator, how the different components work together. This has been done around the year in the 70s, 80s, but more recently in the year 2000, 2010. Especially, it was a strong US effort. This is like a cover of Physics Today at the end of the 90s, I think. But all of these efforts were actually aiming to relatively to much lower energy, for which electron and hadron collider offered just a much better alternative and much easier to realize. What is new now is that this target of multi-TeV energy offers challenges to the existing technologies that really makes it harder and harder to push them. And this sort of becomes a very viable alternative to sort of, if we can master, it becomes really compelling because it allows us to really push it much further. So the way we do it, the way we would know a Muon collider, this is just showing a sort of a schematic view of how such a collider could be realized. And there are different stages. I wanted to just highlight the basic idea and sort of what are the main challenges that go around it. But the overall, as I mentioned at the very beginning, the overall key aspect is that all the challenges go around the fact that the muon is not a stable particle, it's unstable and decays. And this is, if you want, keep it in mind because it will come up as essentially our main challenge throughout. And so the first thing you need to do is produce muons. So how do you produce muons? They come as in cosmic rays, but we need a much larger flux and we need to be able to make a beam of muons. And this is done basically hitting one of the ways that the most efficient ways we know is actually taking protons from hydrogen and then colliding them to a target, and that produces pions, which is another particle made of quarks that actually decays pretty quickly to muons and neutrinos. And so this is essentially the way we produce muons. So these protons hit a target, pions are captured from a magnetic field and let them decay to muons. And in fact, being able to sort of capture this muon that come from this chain reaction is a non-trivial task to achieve with high efficiency and require both a short intense proton beam to have enough rate of muons produced and a very large and very powerful solenoid to capture these muons and keep them essentially within our tunnel, if you want, our pipe. So step 2 is once you have this muon, they will be sort of going a bit all around the places. So you will have a kind of beam that will be like this size. Now you want to shrink it down to something like micrometer size and having a momentum spectrum that is very homogeneous, very monochromatic. And all conventional ways to do that actually fail miserably just because the muon, you don't have much time. The muons will decay and will disappear pretty quickly. And so the best way we found so far is actually a very different way in which we pass a muon through some absorber, so usually light absorber like hydrogen, that essentially from the muon, the original muon momentum, it reduces its momentum, and then we accelerate along the line we are interested, restoring part of the momentum longitudinally. And so this essentially transforms each muon momentum from something like that to something a little bit closer like that. And we repeat many, many times to try to essentially make it monochromatic and focused. This is actually a really critical part of a Muon collider concept. It's very new in accelerator physics. And in fact, it's regarded as the main aspect of a Muon collider that should really be demonstrated experimentally to gain experience of how to do that in an efficient way. And this is, in fact, this topic is the aspect of a demonstrator facility proposal, which is proposed to be constructed either at Fermilab in Chicago or at CERN to operate, let's say, the beginning of the 30s with a pretty stiff cost, but is still a relatively small cost compared to the full facility. But this is regarded as a sort of a huge stepping stone in the feasibility of a Muon collider. So now we have this beam of muons. And this beam of muons essentially goes through a set of accelerator rings that accelerates them more and more. And by the time they are in these large accelerators, and so these essentially need to be injected here and then very quickly accelerated, and then they get transferred in a final ring where they get to collide. And in this actually is, quote, the relatively simpler part, although it still requires very, very fast magnet that can ramp up and down hundreds of Tesla per second, and strong superconducting magnets to contain and focus this muon, which is also still beyond the current technology, but is something that we have a strong R&D towards. And just to give an idea, so we said that the muons decay very quickly. So how quickly? Well, what comes in our advantage is that the more we accelerate, the more velocity they have, the more the lifetime in the lab frame becomes longer, and this by the Lorentz factor gamma. And in fact, by the time they are in the collider ring, and they have about 5 TeV of energy, they don't live anymore in our lab frame. They will live about 0.1 second. Not that much, much better than 2 microseconds. So that is something we can work with. And in fact, the idea is essentially to keep topping up these muons every about 0.2 seconds, so at 5 times per second. And so this is essentially how, in some arbitrary units, the number of muons that are brought to collision will look like. It will just go down very quickly, the axis is in seconds, and then will be topped up, down, up, and so on, so forth. So we will get to create new muon bunches and put them in the ring at around 5 Hertz. Okay, so finally, we have our muons, and they are colliding. So, so we are almost done with one other important caveat, which is again connected with the fact that the muons are decaying. As we bring them to collisions, parts of this muon will decay, and we will have this high energy electron that comes as a cloud together with the muon beam. And so we need to put some essentially dedicated shielding that is usually expected to be tungsten-based to contain some part of this high energy electron. But, and then we need to design detectors around the interaction point to detect the output of this reaction that they can essentially separate the identification of the reaction products of the muon from part of this high energy electron that through the shielding will not be completely absorbed, but will enter the detector region. And in fact, such background is what we call beam-induced background. So this gives you another view. This is the line where the beam would come through. This is the nominal interaction point. This color cylinder would represent sort of how we put our instrumentation to detect the decay, the reaction products of the muon-muon collision. And here there is a zoom in of how one high energy electron would basically hit a tungsten shielding, and within it would be partially absorbed with just a little bit of leakage. However, this is just depicting how one electron will look like. And instead, we will have about 10 millions of these happening at every time. And so what that looks like around the interaction point is something more like that. Every line in it shows essentially one particle produced around the interaction point, which you see is pretty crowded, so you can't even see where exactly it is. So we'll have many particles flying around that essentially kind of mask what is happening in our muon-muon collision. And part of our effort is trying to figure out instrumentation that allow us to basically take these things apart and distinguish what comes from the muon-muon interaction. And to make things worse, what is depicted here is actually 0.0003% of the actual occupancy from this type of background that we need to deal with. So it's an interesting challenge, but a challenge we are ready to meet. And in fact, there are already a couple of different detector instrumentation concepts that can work in a 10 TeV muon collider that have conceptual designs. This is one example. In general, you see this is again the beam line, and this sort of onion-like structure is essentially a set of different technology of the detector that are made to essentially identify different interaction final state particles from the muon-muon collisions, and being able to enable us to do the measurements I mentioned at the beginning that we care about. So we have conceptual design of this, but it's a talk by itself about what entails to do that. I wanted just to mention one example, which is the innermost part of this type of instrumentation. Is tasked to detect charged particles. So, and it needs to do that with the minimal disruption of the trajectory of this particle that get produced. And it needs to do that disentangling from all these different other particles that are produced from this high energy electron that come into the detector region as well. Well, lucky enough, we expect this is envisioned to be done through a solid state detector that is pixelated with very, very small granularity, that has high accuracy in timing. It also needs to be very light to disturb this particle very little. It needs to be radiation hard because it's a very high radiation area around the interaction point. And in addition to that, we need to have dedicated front-end electronics with a large bandwidth. So that's overall a pretty demanding set of requirements, but lucky enough, we have a pretty long-standing expertise in building such detector and colliders for really decades at this point. And in fact, even here at LBL, we have a lot of R&D going on, which touches many aspects that will be critical for a detector in a muon collider that goes from reconstruction algorithm, data transmission, dedicated electronics for front-end electronics, lightweight structures, readout technology and software, and even new material for this type of solid-state detectors. Okay, so this was to give you a little bit of a feeling of what are parts of the challenges that we'll have to face to make it happen. And now the very last part, I wanted to tell you a little bit of when and where such a collider could be realized. So to do that, I wanted to mention, so how are we figuring out all these various parts? We have an international collaboration, which is called IMCC, or International Muon Collider Collaboration, which is, I would say, the most recent push to get a design for such a collider. This was set up by CERN in 2021 for exploring the feasibility of a multi-TV muon-muon collider. It has many institutions, many hundreds of physicists and engineers working. In particular, here on the right, you see the US contribution about the US university, and we also have people from laboratories collaborating with this collaboration, although we are technically not yet part of the collaboration until the Department of Energy signs an explicit agreement. In addition, however, in the US, we are trying to sort of bring up a community that is interested in these projects. And so last year, we had actually a so-called inaugural US Muon Collider meeting for this type of multi-TV collider. It was a very nice meeting we had at Fermilab. We managed to bring together accelerator physicists, detector instrumentation expert, and theoretical physicists to essentially brainstorm together what is the best compromises and what are the best choices to bring a muon collider together. And that has been pretty successful. This pie chart just shows you the mix in terms of, like, as I said, detector instrumentation expert, accelerator physicist, theorist. And here it shows you the different career stages from postdoc to senior people to graduate students. We had a very broad slice of attendee. And overall, we had about 230 people that attended in person. Here is a picture, and a few tens more that were remote. So it was very nice. So it's a pretty vibrant community also in the US that is sort of ready to take on this challenge. Okay, but let me tell you just briefly about when such a collider could be realized. And there should be no surprise that it will take time. This is just to give you an auto comparison. This is the latest E plus E minus collider we ever had, and the latest hadron collider we ever built, the LHC. And each of them sort of, this type of project takes about around 20 years from when you start designing them to actually when you finish constructing and taking data. And a muon collider will not be an exception. That will take at least a couple 20 years to essentially finish all the R&D phase, deciding to construct and start building such a collider. Being more specific is hard until we choose a project like that is approved and a site is chosen, because then there are constraints depending on what other projects are ongoing. But this is the type of timescale we are looking for realizing such a collider. The other thing is where. as I said, the development depends on the site, so where could we build such a collider? And there are two main sites that are being considered. One is in Chicago at the Fermi National Accelerator Laboratory, or Fermilab. And in fact, a 10 TeV collider basically just fits exactly the existing boundary on the Fermilab laboratory. And so it has the possibility to bring the energy frontier back in the US. The other very interesting possibility and very compelling is actually to build it at CERN, where one could actually reuse the LHC tunnel, and one would need to just an extra small tunnel for realizing a 10 TeV collider. So that is also a very attractive option. And that could follow after the end of the LHC. Okay, so in finishing, I just wanted to say that there is really a lot of local expertise here between UC Berkeley and LBL that works on present and future collider. And maybe not all of you are aware of all of it, but we have a so-called ATAP, or Accelerator Technology and Applied Physics Division at LBL, that has lots of expertise about advanced accelerator technique and next generation magnets. I talked a lot about magnets in this colloquium, so we have a lot of expertise here. And we have a UC Berkeley LBL Physics and Computing Division, which is very active in the ATLAS experiment, but also is very active in detector R&D for both LHC upgrades as well as future collider, advanced algorithm for and parallelization on HPC, high-performance computing clusters, and also a theory group that is very active in studying the physics case for such future collider. So this is just an example. This is just the ATLAS group up, the UC Berkeley BNL. We most of the time stay up in the lab, but if you don't know us, you're welcome to visit us anytime. And we have a set of staff, postdocs, and we have also, including 10 UC Berkeley graduate students, and every time we have more than 10 undergrad students doing research with us at any given time. So this brings me to the conclusion. So I presented you as an outline of why we need the Muon Collider. And I guess the first summary is that the potential is to have a flexible tool that allows to push the frontier of elementary particle physics. How we're going to build it, there are well-developed ideas, but also well-identified challenges that require creativity and serious investment to be overcome. And then when and how the community support is strong here, but the project timelines very clearly, as in this type of project, are at the level of 20 to 30 years. And CERN and Fermi are two of the most obvious places where such a collider could be realized. So overall, I would conclude just say that for me, this type of project is a new, very exciting prospect, and it's especially true for young scientists that essentially want to have a new, unbiased look to this field and want to contribute on how to innovate this field in the future. Thank you.
All right, thanks a lot, Simone. So do we have any questions? Why don't we start over there?
Yes, that's a great question. And so essentially, even more, I'll repeat the question now, and I'll bring up the pictures so that, okay. So you see that the largest ring, there are two different rings. And one is bigger and one is smaller. And the question is, why do we need these two rings? Why you don't have just one big ring, okay? And in fact, funny enough, the collisions happen in this slightly smaller ring. Okay, you would expect while you keep accelerating things, you might need bigger and bigger ring, and then you make the collision in the biggest ring, which is what we do in the proton-proton collisions. But here, the reason is that the bigger ring is needed in the acceleration phase because we need to keep injecting these muons. So we need magnets to sort of go up and down to kick in the muons, and we need to keep them in the ring. So the best compromise in not losing too many muons and accelerate them well enough to keep the focus is to have a bigger ring. Once they are well focused and a small beam and accelerated to the desired energy, keeping them ring would be not great because now it takes more time for them to go around, okay? And so by the time they go around, we lose many of them, okay? So now it's much better to inject them in a smaller ring where we can put different type of magnets which will focus them the best for the collisions, and will take less time for them to go around the ring, and we can get the most collisions out of them before they run out.
So the big ring, the magnet's ramp.
For the bigger rings, it's mostly about how fast the magnets need to ramp, and there are some consideration about optics of sort of keeping the beam inside that is not as compatible to then creating magnets to sort of focus the beam for collisions. So it's much better to have a second ring, which has a different type of magnets to focus for the collision. And at that point, you want to make it smaller to get the best out of that in terms of how many collisions before you finish those muons, they decay.
All right, so there's a question there.
Yes.
At the end, it seems that you're suggesting that we are going to construct a collider reaching the energy scale of 10 electrons.
Yeah. Which seems very, actually lower than the 14 TeV of the LHC. So this goes back to this. Actually, let me, I think I have one plot that I put in backup because it's more complicated, but I wanted to show you. So there are two reasons why that is important. One is signal, so reactions we are interested in, okay? This plot, there are a lot of caveats, but follow me for just a second. It shows you essentially the rate of producing different type of signal divided. These are, like, for instance, 2-to-2 processes as a function of the center of mass for a proton-proton collider on the y-axis, and what is the equivalent rate, when do you get the equivalent rate, as a function of the center of mass of a muon-muon collider. And so essentially, these bands kind of guide your eye to show you that a 50 to 100 TeV proton-proton collider produces the same rate for these processes of a 3 to 10, 15 TeV muon-muon collider. So you need much lower energy because it's a fundamental particle, it's an elementary particle versus a composite particle. And so the composite particle, you will just essentially hit some constituents, and the efficiency of that energy is much lower in practice. Of the actual fundamental reaction you're probing is much lower. The efficiency of your fundamental scale you're probing is lower in a proton-proton because it's a composite particle. The second side of that story is actually background. So what reaction with a similar final state, how many of them get produced? And so the right shows you an example where, for instance, we want to study, I don't know, a Higgs boson production. And the reason it's so hard at LHC is that most of the reactions have absolutely nothing to do with the Higgs boson. Okay, the probability of producing a Higgs boson in a PP collision versus anything else, we are talking about something that is 10 to the minus 10. Okay, and we need to try to isolate those. So we need to reject 10 to the 10 different type of reaction, which some of them look very similar, to find a Higgs boson. In a muon collider is percent level. So the type of backgrounds we have is actually very different. The type of similar reaction is very different. It's a much cleaner machine to study the reactions we want. And so when you put all of these together, the rough equivalence is to a 10 TeV muon is similar to a 100 TeV proton-proton, roughly. Then there are always cases you can find one is better than the other, but roughly speaking.
All right, question in the back there.
How does the Higgs field, the Higgs potential influence muon-muon scattering?
Yes, so essentially, the question is how the Higgs potential is connected with a muon-muon scatter, right? And essentially, the key is essentially measuring the rate of interaction of Higgs with itself, and through that, we can constrain part of the shape of the potential. And practically speaking, in a muon-muon collision, this is another aspect which I hadn't at the time, but in fact, when we say we create a muon collider, what I like to say, what we are actually happening is very often when these two muon collide, they practically emit either photon or the mediator of the weak force, W and Z bosons, and those are essentially the main driver of the interaction. So we basically can produce Higgs boson, 1, 2, or 3, or 4 Higgs boson based on this type of thing. 4 is too rare, but 1, 2, or 3 Higgs boson. And so we're essentially looking at the rate of this interaction where we have multiple Higgs boson produced, how they distribute, and so on. That's how we can basically constrain that type of potential. But it's an extremely, extremely rare occurrence. It's a rare reaction. So that's why we need to also not only have the increases, its rate increases with energy, so high energy helps, but at the same time, we need lots of these collisions because it's extremely rare. That in a few words, there are a lot more details, yeah.
All right, at the back there.
Okay, so the question is if there are existing E plus E minus or other type of colliders that can be recycled to basically host a Muon collider. So people have been looking into that, and in fact, things are evolving, and ideas come every day. You know, if I had given this colloquium 6 months ago, the most at that time we thought that even at CERN, the LHC tunnel could not be reused for a Muon collider. It didn't work. 6 months later, now we have an actual working conceptual design that reuses the LHC ring and just requires a small one. Fermilab, we currently have no design that reuses existing ring that are the Tevatron for hosting a Muon collider, and we require all new, basically, tunnels to be excavated. Does that mean that it's not possible? I think also depends on how much people look into these things. Other than that, I don't think we have anything else I can think of that is big enough that could fit the purpose.
All right, let's take that question there.
So the time to accelerate the proton from the colliders is much higher than the lifetime of Muon, right? So isn't it like the hardest thing to achieve to actually be so fast to accelerate Muon? So
yeah,
you'd say that there are other bigger.
Yeah, the thing is in some sense, one of the most critical part, I would say, is early in the process, because the slower they are, the faster they decay in your lab frame. So the first part, when we sort of produce Muon that are relatively slow compared to the final energies, is where we need to be the fastest. And that's why sort of that part is sort of grabs this Muon that come from pion decays and sort of go in all directions and need to create a focus, a relatively narrow beam that then can be accelerated, is the part that sort of cannot waste any time. And where conventional ways to sort of clean up your beam and make it nice will not work because they're just too slow. And that's why this idea is back probably 20 years, but has changed in nature a little bit recently. That's how people are thinking about this set of absorbers and acceleration cells that allow to actually achieve that in a very short time. So that, I would say, is the most critical part, because it's where they're still relatively slow. Like sort of their beta gamma is around 1 at that stage. They are a momentum around 200 MeV. So they're still relatively slow, and so it is the most critical part. Afterwards, in the acceleration ring, yes, it is still critical to not waste time, but actually there, one of the big things is try to accelerate them not only quickly, but without losses, meaning like without having too many muons that go out of the beam as you focus it to keep it in the ring.
Conceptually, it was demonstrated that it should be actually possible.
So
we are still searching for ideas.
That's a great question. So let me tell you, I would say both, in the sense that, let's see if I can, who knows if I, yeah. There was actually an experiment that was set up at Fermilab, okay, and that has published actually the latest results in 2024 that exactly try to do that. That's a picture of that setup. Try to take muons and basically pass them through this absorber, accelerate them, and show that in principle, they could basically narrow down, reduce what they call the emittance, so the size of the beam, and make it more, let's say, narrow and uniform. And this is what the plot is trying to show, in which it shows essentially the reduction of emittance with and without absorber and compares to the simulation and shows a reduction of the emittance. Now, there is one catch, that this is sort of proving it and not proving at the same time, because it's been done one muon at a time, and then shows that statistically, if you extrapolate too many muons together, you would get what you need. The reason we want to have a demonstrator facility is to prove it with a complete set, so with including beam effects, so with an actual bunch of muons. And because essentially, as you progressively go through these sort of cycles of like slowing down and reaccelerating, the configuration of these elements that combine a magnetic field and a radio frequency cavity for acceleration becomes more and more complicated. And so studying experimentally how well the tolerances and configuration like that can be realized experimentally is non-trivial to simulate. And I think and what you lose if you don't do it right is that you lose muons. So it's a question of like, from that many muons I start from, how many do I end with? And so trying to show experimentally that your efficiency is high enough determine essentially the final luminosity of your collider, so the final rate of interactions you will have. So there has been already some demonstration, but we think more would be best to be able to figure out what's the ultimate performance of that type of collider.
All right, I think we're going to cut off. I know there are more questions. I think we're going to wrap up here. And thanks to Simone again. And I'm sure he's happy to chat to anybody who wants to. So thank you very much.
Thank you.